Brass.
Brass is an alloy made of copper and zinc. The proportions of zinc and copper can be varied to create a range of brasses with varying properties. It is a substitutional alloy. Atoms of the two constituents may replace each other within the same crystal structure. By comparison, bronze is principally an alloy of copper and tin. Bronze does not necessarily contain tin, and a variety of alloys of copper, including alloys with arsenic, phosphorus, aluminium, manganese, and silicon, are commonly termed bronze. The term is applied to a variety of brasses and the distinction is largely historical, both terms having a common antecedent in the term Latin. It is used for decoration for its bright gold-like appearance. For applications where low friction is required such as locks, gears, bearings, doorknobs, ammunition casings and valves. For plumbing and electrical applications. And extensively in brass musical instruments such as horns and bells for its acoustic properties. It is also used in zippers. Brass is often used in situations where it is important that sparks not be struck, as in fittings and tools around explosive gases.
Properties.
The malleability and acoustic properties of brass have made it the metal of choice for musical instruments such as the trombone, tuba, trumpet, cornet, baritone horn, euphonium, tenor horn, and French horn, which are collectively known as brass instruments. Even though the saxophone is classified as a woodwind instrument and the harmonica is a free-reed aerophone, both are also often made from brass. In organ pipes of the reed family, brass strips, called tongues, are used as the reeds, which beat against the shallot, or beat through the shallot in the case of a free reed. Although not part of the brass section, snare drums are also sometimes made of brass. Brass has higher malleability than bronze or zinc. The relatively low melting point of brass, 900 to 940 DEGC, 1652 to 1724 DEGF, depending on composition, and its flow characteristics make it a relatively easy material to cast. By varying the proportions of copper and zinc, the properties of the brass can be changed, allowing hard and soft brasses. The density of brass is approximately 303 pounds per cubic inch, 8.4 to 8.73 grams per cubic centimeter. Today almost 90% of all brass alloys are recycled. Because brass is not ferromagnetic, it can be separated from ferrous scrap by passing the scrap near a powerful magnet. Brass scrap is collected and transported to the foundry where it is melted and recast into billets. Billets are heated and extruded into the desired form and size. Aluminium makes brass stronger and more corrosion resistant. Aluminium also causes a highly beneficial hard layer of aluminium oxide, Al2O3, to be formed on the surface that is thin, transparent and self-healing. Tin has a similar effect and finds its use especially in seawater applications, naval brasses. Combinations of iron, aluminium, silicon and manganese make brass wear and tear resistant.
Lead content.
To enhance the machinability of brass, lead is often added in concentrations of around 2%. Since lead has a lower melting point than the other constituents of the brass, it tends to migrate towards the grain boundaries in the form of globules as it cools from casting. The pattern the globules form on the surface of the brass increases the available lead surface area, which in turn affects the degree of leaching. In addition, cutting operations can smear the lead globules over the surface. These effects can lead to significant lead leaching from brasses of comparatively low lead content. Silicon is an alternative to lead. However, when silicon is used in a brass alloy, the scrap must never be mixed with leaded brass scrap because of contamination and safety problems. In October 1999, the California State Attorney General sued 13 key manufacturers and distributors over lead content. In laboratory tests, state researchers found the average brass key, new or old, exceeded the California Proposition 65 limits by an average factor of 19, assuming handling twice a day. In April 2001, manufacturers agreed to reduce lead content to 1.5%, or face a requirement to warn consumers about lead content. Keys plated with other metals are not affected by the settlement, and may continue to use brass alloys with higher percentage of lead content. Also in California, lead-free materials must be used for each component that comes into contact with the wetted surface of pipes and pipe fittings, plumbing fittings and fixtures. On January 1, 2010, the maximum amount of lead in lead-free brass in California was reduced from 4% to 0.25% lead. The common practice of using pipes for electrical grounding is discouraged, as it accelerates lead corrosion.
Corrosion-resistant brass for harsh environments.
The so-called dezincification-resistant, DZ or drive, brasses are used where there is a large corrosion risk and where normal brasses do not meet the standards. Applications with high water temperatures, chlorides present, or deviating water qualities, soft water, play a role. DZ brass is excellent in water boiler systems. This brass alloy must be produced with great care, with special attention placed on a balanced composition and proper production temperatures and parameters to avoid long-term failures.
Germicidal and antimicrobial applications.
The copper in brass makes brass germicidal. Depending upon the type and concentration of pathogens and the medium they are in, brass kills these microorganisms within a few minutes to hours of contact. The bactericidal properties of brass have been observed for centuries and were confirmed in the laboratory in 1983. Subsequent experiments by research groups around the world reconfirmed the antimicrobial efficacy of brass, as well as copper and other copper alloys. See antimicrobial copper alloy touch surfaces. Extensive structural membrane damage to bacteria was noted after being exposed to copper. In 2007, U.S. Department of Defense's Telemedicine and Advanced Technology Research Center, TATRC, began to study the antimicrobial properties of copper alloys, including four brasses, C87610, C69300, C26000, C46400, in a multi-site clinical hospital trial conducted at the Memorial Sloan Kettering Cancer Center, New York City, the Medical University of South Carolina, and the Ralph H. Johnson VA Medical Center, South Carolina. Commonly touched items, such as bed rails, over-the-bed tray tables, chair arms, nurses' call buttons, 4-poles, etc. were retrofitted with antimicrobial copper alloys in certain patient rooms, that is, the coppered rooms, in the intensive care unit, ICU. Early results disclosed in 2011 indicate that the coppered rooms demonstrated a 97% reduction in surface pathogens versus the non-coppered rooms. This reduction is the same level achieved by terminal cleaning regimens conducted after patients vacate their rooms. Furthermore, of critical importance to healthcare professionals, the preliminary results indicated that patients in the coppered ICU rooms had a 40.4% lower risk of contracting a hospital-acquired infection versus patients in non-coppered ICU rooms. The U.S. Department of Defense investigation contract, which is ongoing, will also evaluate the effectiveness of copper alloy touch surfaces to prevent the transfer of microbes to patients and the transfer of microbes from patients to touch surfaces, as well as the potential efficacy of copper alloy-based components to improve indoor air quality. In the U.S., the Environmental Protection Agency regulates the registration of antimicrobial products. After extensive antimicrobial testing according to the agency's stringent test protocols, 355 copper alloys, including many brasses, were found to kill more than 99.9% of methicillin-resistant Staphylococcus aureus, MRSA, E. coli 0157, H7, Pseudomonas aeruginosa, Staphylococcus aureus, Enterobacter erogens, and vancomycin-resistant Enterococci, VRE, within 2 hours of contact. Normal tarnishing was found not to impair antimicrobial effectiveness. Antimicrobial tests have also revealed significant reductions of MRSA as well as 2 strains of epidemic MRSA, EMRSA1 and EMRSA16, on brass, C24000 with 80% Cu, at room temperature, 22 DEGC, within 3 hours. Complete kills of the pathogens were observed within 4.5 hours. These tests were performed under wet exposure conditions. The kill time frames, while impressive, are nevertheless longer than for pure copper, where kill time frames ranged between 45 to 90 minutes. A novel assay that mimics dry bacterial exposure to touch surfaces was developed because this test method is thought to more closely replicate real-world touch surface exposure conditions. In these conditions, copper alloy surfaces were found to kill several million colony-forming units of Escherichia coli within minutes. This observation, and the fact that kill time frames shorten as the percentage of copper in an alloy increases, is proof that copper is the ingredient in brass and other copper alloys that kills the microbes. The mechanisms of antimicrobial action by copper and its alloys, including brass, is a subject of intense and ongoing investigation. It is believed that the mechanisms are multifaceted and include the following: 1. Potassium or glutamate leakage through the outer membrane of bacteria. 2. Osmotic balance disturbances. 3. Binding to proteins that do not require or utilize copper. 4. Oxidative stress by hydrogen peroxide generation. Research is being conducted at this time to determine whether brass, copper, and other copper alloys can help to reduce cross-contamination in public facilities and reduce the incidence of nosocomial infections, hospital-acquired infections, in healthcare facilities. Also, owing to its antimicrobial algacidal properties that prevent biofouling, in conjunction with its strong structural and corrosion-resistant benefits for marine environments, brass alloy netting cages are currently being deployed in commercial-scale aquaculture operations in Asia, South America, and the USA.
Season cracking.
Brass is susceptible to stress corrosion cracking, especially from ammonia or substances containing or releasing ammonia. The problem is sometimes known as season cracking after it was first discovered in brass cartridge cases used for rifle ammunition during the 1920s in the Indian Army. The problem was caused by high residual stresses from cold forming of the cases during manufacture, together with chemical attack from traces of ammonia in the atmosphere. The cartridges were stored in stables and the ammonia concentration rose during the hot summer months, thus initiating brittle cracks. The problem was resolved by annealing the cases, and storing the cartridges elsewhere.
History.
Although forms of brass have been in use since prehistory, its true nature as a copper-zinc alloy was not understood until the post-medieval period because the zinc vapor which reacted with copper to make brass was not recognized as a metal. The King James Bible makes many references to brass. The Shakespearean English form of the word brass can mean any bronze alloy, or copper, rather than the strict modern definition of brass. The earliest brasses may have been natural alloys made by smelting zinc-rich copper ores. By the Roman period, brass was being deliberately produced from metallic copper and zinc minerals using the cementation process, and variations on this method continued until the mid-19th century. It was eventually replaced by speltering, the direct alloying of copper and zinc metal which was introduced to Europe in the 16th century.
Early copper-zinc alloys.
In West Asia and the Eastern Mediterranean, early copper-zinc alloys are now known in small numbers from a number of 3rd millennium BC sites in the Aegean, Iraq, the United Arab Emirates, Kalmykia, Turkmenistan and Georgia, and from 2nd millennium BC sites in West India, Uzbekistan, Iran, Syria, Iraq and Israel. However, isolated examples of copper-zinc alloys are known in China from as early as the 5th millennium BC. The compositions of these early brass objects are very variable and most have zinc contents of between 5% and 15% Wt, which is lower than in brass produced by cementation. These may be natural alloys manufactured by smelting zinc-rich copper ores in redox conditions. Many have similar tin contents to contemporary bronze artifacts, and it is possible that some copper-zinc alloys were accidental and perhaps not even distinguished from copper. However, the large number of copper-zinc alloys now known suggests that at least some were deliberately manufactured, and many have zinc contents of more than 12% Wt, which would have resulted in a distinctive golden color. By the 8th–7th century BC, Assyrian cuneiform tablets mention the exploitation of the copper of the mountains, and this may refer to natural brass, Aurichalcos, the ancient Greek translation of this term, was later adapted to the Latin aurichalca meaning gold and copper, which became the standard term for brass. In the 4th century BC, Plato knew aurichalcos as rare and nearly as valuable as gold, and Pliny describes how aurichalcum had come from Cypriot or deposits which had been exhausted by the 1st century AD.
Brass making in the Roman world.
During the later part of 1st millennium BC, the use of brass spread across a wide geographical area, from Britain and Spain in the west to Iran and India in the east. This seems to have been encouraged by exports and influence from the Middle East and Eastern Mediterranean, where deliberate production of brass from metallic copper and zinc ores had been introduced. The 4th century BC writer Theopompus, quoted by Strabo, describes how heating earth from Andira in Turkey produced droplets of false silver, probably metallic zinc, which could be used to turn copper into aurichalcos. In the 1st century BC, the Greek Dioscoride seems to have recognized a link between zinc minerals and brass, describing how cadmia, zinc oxide, was found on the walls of furnaces used to heat either zinc or copper, and explaining that it can then be used to make brass. By the 1st century BC, brass was available in sufficient supply to use as coinage in Phrygia and Bithynia, and after the Augustan currency reform of 23 BC it was also used to make Roman dupondii and cestatur. The uniform use of brass for coinage and military equipment across the Roman world may indicate a degree of state involvement in the industry, and brass even seems to have been deliberately boycotted by Jewish communities in Palestine because of its association with Roman authority. Brass was produced by the cementation process, where copper and zinc ore are heated together until zinc vapor is produced, which reacts with the copper. There is good archaeological evidence for this process, and crucibles used to produce brass by cementation have been found on Roman period sites including Xanten and Nidda in Germany, Lyon in France, and at a number of sites in Britain. They vary in size from tiny acorn size to large amphorae-like vessels, but all have elevated levels of zinc on the interior and are lidded. They show no signs of slag or metal prills, suggesting that zinc minerals were heated to produce zinc vapor, which reacted with metallic copper in a solid-state reaction. The fabric of these crucibles is porous, probably designed to prevent a build-up of pressure, and many have small holes in the lids which may be designed to release pressure or to add additional zinc minerals near the end of the process. Dioscorides mention that zinc minerals were used for both the working and finishing of brass, perhaps suggesting secondary additions. Brass made during the early Roman period seems to have varied between 20% to 28% Wt zinc. The high content of zinc in coinage and brass objects declined after the 1st century AD, and it has been suggested that this reflects zinc loss during recycling and thus an interruption in the production of new brass. However, it is now thought this was probably a deliberate change in composition, and overall the use of brass increases over this period, making up around 40% of all copper alloys used in the Roman world by the 4th century AD.
Brass making in the medieval period.
Little is known about the production of brass during the centuries immediately after the collapse of the Roman Empire. Disruption in the trade of tin for bronze from Western Europe may have contributed to the increasing popularity of brass in the East, and by the 6th–7th centuries AD over 90% of copper alloy artifacts from Egypt were made of brass. However, other alloys such as low tin bronze were also used, and they vary depending on local cultural attitudes, the purpose of the metal and access to zinc, especially between the Islamic and Byzantine world. Conversely, the use of true brass seems to have declined in Western Europe during this period in favor of gunmetals and other mixed alloys, but by the end of the 1st millennium AD brass artifacts are found in Scandinavian groves in Scotland. Brass was being used in the manufacture of coins in Northumbria, and there is archaeological and historical evidence for the production of brass in Germany and the Low Countries, areas rich in calamine ore. These places would remain important centers of brass making throughout the medieval period, especially Dinant. Brass objects are still collectively known as dinanterie in French. The baptismal font at St. Bartholomew's Church, Liege in modern Belgium, before 1117, is an outstanding masterpiece of Romanesque brass casting. The cementation process continued to be used, but literary sources from both Europe and the Islamic world seem to describe variants of a higher temperature liquid process which took place in open-topped crucibles. Islamic cementation seems to have used zinc oxide known as tritiya or tuti rather than zinc ores for brass making, resulting in a metal with lower iron impurities. A number of Islamic writers and the 13th century Italian Marco Polo describe how this was obtained by sublimation from zinc ores and condensed onto clay or iron bars, archaeological examples of which have been identified at Gush in Iran. It could then be used for brass making or medicinal purposes. In 10th century Yemen, al-Hamdani described how spreading al-Gamir, probably zinc oxide, onto the surface of the molten copper produced tutia vapor which then reacted with the metal. The 13th century Iranian writer al-Kashani describes a more complex process whereby tritiya was mixed with raisins and gently roasted before being added to the surface of the molten metal. A temporary lid was added at this point, presumably to minimize the escape of zinc vapor. In Europe a similar liquid process in open-topped crucibles took place, which was probably less efficient than the Roman process, and the use of the term tuti by Albertus Magnus in the 13th century suggests influence from Islamic technology. The 12th century German monk Theophilus described how preheated crucibles were 1/6 filled with powdered calamine and charcoal, then topped up with copper and charcoal before being melted, stirred, then filled again. The final product was cast, then again melted with calamine. It has been suggested that this second melting may have taken place at a lower temperature to allow more zinc to be absorbed. Albertus Magnus noted that the power of both calamine and tuti could evaporate and described how the addition of powdered glass could create a film to bind it to the metal. German brass-making crucibles are known from Dortmund dating to the 10th century AD and from Soest and Schwert in Westphalia dating to around the 13th century confirm Theophilus' account, as they are open-topped, although ceramic discs from Soest may have served as loose lids which may have been used to reduce zinc evaporation, and have slag on the interior resulting from a liquid process.
Brass making in Renaissance and post-medieval Europe.
The Renaissance saw important changes to both the theory and practice of brass making in Europe. By the 15th century there is evidence for the renewed use of lidded cementation crucibles at Zwickau in Germany. These large crucibles were capable of producing 20 kilograms of brass. There are traces of slag and pieces of metal on the interior. Their irregular composition suggesting that this was a lower temperature, not entirely liquid process. The crucible lids had small holes which were blocked with clay plugs near the end of the process, presumably to maximize zinc absorption in the final stages. Triangular crucibles were then used to melt the brass for casting. 16th century technical writers such as Birinux, Urca and Agricola described a variety of cementation brass making techniques and came closer to understanding the true nature of the process, noting that copper became heavier as it changed to brass and that it became more golden as additional calamine was added. Zinc metal was also becoming more commonplace by 1513. Metallic zinc ingots from India and China were arriving in London, and pellets of zinc condensed in furnace flues at the Rammelsberg in Germany were exploited for cementation brass making from around 1550. Eventually it was discovered that metallic zinc could be alloyed with copper to make brass, a process known as speltering, and by 1657 the German chemist Johann Glauber had recognized that calamine was nothing else but unmeltable zinc, and that zinc was a half-right metal. However, some earlier high zinc, low iron brasses such as the 1530 Whiteman brass memorial plaque from England may have been made by alloying copper with zinc and include traces of cadmium similar those found in some zinc ingots from China. However, the cementation process was not abandoned, and as late as the early 19th century there are descriptions of solid-state cementation in a domed furnace at around 900 to 950 DEGC and lasting up to 10 hours. The European brass industry continued to flourish into the post-medieval period, buoyed by innovations such as the 16th century introduction of water-powered hammers for the production of battery wares. By 1559 the German city of Aachen alone was capable of producing 300,000 hundredweights of brass per year. After several false starts during the 16th and 17th centuries, the brass industry was also established in England, taking advantage of abundant supplies of cheap copper smelted in the new coal-fired reverberatory furnace. In 1723, Bristol brass maker Nehemiah Champion patented the use of granulated copper, produced by pouring molten metal into cold water. This increased the surface area of the copper, helping it react, and zinc contents of up to 33% Wt were reported using this new technique. In 1738, Nehemiah's son William Champion patented a technique for the first industrial-scale distillation of metallic zinc known as distillation per desencum, or the English process. This local zinc was used in speltering and allowed greater control over the zinc content of brass and the production of high zinc-copper alloys, which would have been difficult or impossible to produce using cementation, for use in expensive objects such as scientific instruments, clocks, brass buttons and costume jewelry. However, Champion continued to use the cheaper calamine cementation method to produce lower zinc brass, and the archaeological remains of beehive-shaped cementation furnaces have been identified at his works at Warmley. By the mid to late 18th century, developments in cheaper zinc distillation such as John Jack Dunnies horizontal furnaces in Belgium and the reduction of tariffs on zinc, as well as demand for corrosion-resistant high zinc alloys, increased the popularity of speltering, and as a result cementation was largely abandoned by the mid-19th century.